All right, so we're in section 5.3, additional properties of the binomial distribution. And so it starts out with graphing a binomial distribution procedure. On page 208 is up here on the screen for you to take a look at. It'll end up that when you graph it, it's going to be a histogram. So we'll look at the procedure. We'll go over example 6, and then you guys look over guided exercise 6 on page 209. So over here we have the procedure, how to graph a binomial distribution. You have R values on the horizontal axis. That's the number of successes going across. And then the probability of R is going up and down on the vertical axis. You construct a bar over each value of R to extend from R minus 0.5 to R plus 0.5. That means if it's going from negative to positive point or negative positive 0.5 units, the width of the bars is going to equal 1, and the height is going to equal P of R, whatever that happens to be. The area of the bar, the area of the bar is the probability of that particular value of R, because the width is 1, so it's the height that gives you essentially the area. Also, when P is 0.5, your probability of success, you're going to end up with a symmetrical histogram regardless of your sample size. And it turns out that even if P doesn't equal 0.5, as N gets larger and larger, the graph gets more symmetrical. So let's take a look at some stuff here. Example 6. Graph of a binomial distribution. A waiter at the Green Spot restaurant has learned from long experience that the probability that a lone diner will leave a tip is only 0.5, 1/2, right? During one lunch hour, the waiter serves 6 people who are dining by themselves. Make a graph of the binomial probability distribution that shows the probabilities that, let's do this, 0, oh, I'm having trouble with this. 0, 1, 2, 3, 4, 5, or all 6 of the lone diners leave tips. So we're looking at 0, 1, 2, 3, 4, 5, 6. We're going to have 6 bars here because we have 6 trials. So this is a binomial experiment with 6 trials. N equals 6. Success is achieved when the lone diner leaves a tip. So the probability of success is 0.5, which means the probability of failure is also 0.5. So we have N is 6, P is 0.5, and Q is 0.5. P's probability of success, Q's probability of failure. And so what we do is we use table 3 of appendix 2, the binomial table, to find the P of R values for N equals 6 and P equals 0.5. So if you go back to table appendix 2, table 3, they have it here on table, what they've numbered table 2.5. This is what you'll see on that appendix screen for a binomial distribution when N equals 6 and P equals 0.5. So this is going to go from 0 to 6, right? So when R is 0, if you go across and find the corresponding probability under the 0.5 column, you'll get 0.016. If R, your number of successes, is 1, you'll get 0.094. If it's 2, you'll get 0.234. Let's go on down all the way to when it's 6, it'll be 0.016. So these are the heights of our bars in the P of R column, right? And so your graph is going to look like something like this, figure 5.3. This is on page 208, by the way. And so you see how this is these are the number of successes, 0, 1, 2, 3, 4, 5, or 6, right? So those are your R values. Your P of R values are going up the side here. Notice the scale they've used is 0.1, 0.2, 0.3. So they're doing 0.1 units going up the scale. And then they just graph the heights of the bars. And again, you'll notice that the width of these bars is 1. Like 0 plus and minus 0.5 is 1 unit. 1 plus and minus 0.5 is 1, right? 1 unit wide. And so you can graph these in the form of histograms. So back when we were in section 5.1, we saw the formulas for mean and standard deviation of any discrete distribution, and those involve summations and square roots. So, they were a little bit more complex than what you see here in this section, because if it's a binomial distribution, the mean, the expected value mu, just equals n times p. So it's easy to calculate. Sigma squared, that's the variance, is going to be NPQ. So sigma, the standard deviation, is going to be the square root of NPQ. So I'll let you take a look at example 7 on page 211 yourself about calculating these. But when it's a binomial distribution, only 2 possible outcomes, it's really easy to calculate, as you can see from the formulas here. So the last thing that we're going to cover in this section are called quota problems. And so make sure that you look over page 213. I don't know why I put 2 P's there. Delete. Look at page 213, guided exercise 8, finding particular values of n to fit given information. And then example 8, the quota problem, which we're going to look at. You folks make sure you look over guided exercise 8 here on page 212. I'm going to go down to page 214. Now, I had this down at the bottom, but we're passing by it right now to note the procedure on page 214. In other words, if you look at this procedure, how to express binomial probabilities using equivalent formulas, this is important because you're going to essentially be reading word problems, except it involves statistics instead of algebra, like probably what we're used to. So the probability that R is greater than or equal to 1 is the complement of that. 1 minus the probability of 0. That's less than 1, right? It's 1 minus the probability it's less than 1. Probability of at least 2 successes, the probability R greater than or equal to 2, is going to be 1 minus the probability that it's 0 or 1. And then so on all the way up to at least M successes, whatever M has to be in general. The probability R is greater than or equal to M is going to be 1 minus the probability of 0 minus the probability minus, and it keeps on going up to M, right? Or M minus 1, excuse me.